In this video and the videos to come, we're going to add two new tools to our tool bag. The first one is going to be current division, and the second one is going to be voltage division. Now I'm just going to jump into this problem. The problem says find I1 and VO in the circuit. So they give us this circuit. We can see it has two loops, and they want us to find I1, which is the current through this 6K resistor, and they want us to find the voltage VO at these two terminals. Now right away, I want you to be able to recognize something, right? We know this resistor and this voltage VO are going to be in parallel. Tell me, what do we know about parallel voltages? Well, we know if you have something that's in parallel, that means they're going to have the same voltage. So even though this voltage VO is across these two terminals, we know this same exact voltage is also going to be across this 4K resistor. Therefore, I'm just going to label this with the voltage VO as well. I'm going to say plus minus VO. Now let's begin to solve this, right? So right away, what's the first thing you think we should do? Well, there are a few things we can start off with, right? But always remember, if you can combine resistors, you always want to do that. That way you're working with less elements. Especially if you have more than one loop. You always want to go and combine those resistors if you can. So when I look at this, I know I have two resistors here, and these resistors are going to be in series, right? And we know these resistors are series because think about it. Current is going to leave this voltage source, and it's going to go this way. We can label that current I0. Now once it goes this way, it's going to continue to travel through this 2K resistor, and once it reaches this node right here, that current is then going to split, and that current has two parts it can go down. It can go down this 6K resistor, and in the circuit they actually labeled this current as I1, and the current can also go this way, and we can label that current as I2. And we know this current I2 is going to be the same in this 8K and this 4K resistor. Therefore, we know these two resistors are in series, so we can just add them. So when we add these two resistors that are in series, we're going to say 8 plus 4, that's going to give us 12 kilo ohm. So let's redraw this circuit quickly. And we know this resistor right here is just going to be the combination of this 8K and 4K, which is 12K. Now I'm also going to label some currents and voltages. We know the current IO is still going to be flowing this way. That's going to be known as the source current. The current I1 is still through this 6K resistor because we didn't change this at all. And the current I2 still is going to flow in this direction, which is the current flowing through this 8K and the 4K resistor. Now notice the voltage VO is no longer going to be written in our newly drawn circuit once we combine these resistors. Now you must know why. Because the voltage VO is only across this 4K resistor. It is not across this 8K resistor. So when we combine these resistors in series, there is no way we can write back the voltage VO because that voltage is only for this 4K resistor right here. Now we know resistors in series have the same current but not the same voltage. So it's important that we can remember these little tricks as we go along. Okay, let's continue. Okay, so when we look at this, you might decide maybe we can do something now, right, to find I1. But what I would like to do is anytime I can reduce these resistors, I always want to reduce these resistors as much as possible. So I can see I have this 6K resistor and this 12K resistor, and I know these two resistors are in parallel. So because these resistors are in parallel, I'm going to find the parallel combination of these resistors. I'm going to have 12 times 6 over 12 plus 6. 12 times 6, 12 plus 6 is going to give me 4. So we got 4 kilo ohm. Now when I redraw this circuit once again, I'm going to have the newly drawn circuit to look like this. And we know this resistor is going to be 4K. Now let's see if any of our currents or voltages we had labeled is going to be also labeled in our newly drawn circuit once we combined those resistors. Well, we know the current IO, which is the voltage source, is still going to be the current flowing this direction. Now the current I1 and I2 are no longer present, right? Once we combine these two resistors, this resistor is actually now in series with this 2K resistor, which means the current IO, which is flowing through the source and the 2K resistor, is now also going to be flowing through this 4K resistor. Therefore, this is the simplest our circuit can get. Let's just find IO using Ohm's law. So I'm going to use Ohm's law to find IO. I'm going to say IO equals voltage over resistance. The overall voltage in this circuit is going to be 12 volts. We got that from our source. Now we have a 2K resistor plus a 4K resistor. When we combine those two resistors, we're going to get 6K. So the equivalent resistor is just going to be a 6K resistor. I'm just going to write 6,000 for 6K. Now when you solve for this, IO is going to equal 2 milliamp. So this is the current going through this 12 volt source. Now we don't know whether we're going to need this current. The problem wanted us to find I1 and the voltage VO. So this current IO, it might be helpful and it might allow us to solve different parts of the circuit. Sometimes you just have to go through these problems and solve for different things, and then maybe as you continue to analyze the circuit, those things that you solve for might be useful to you. So I'm just going to circle this because it might be useful to us later on. Now when I look at this, I also notice something, right? This is a perfect voltage division problem. Perfect. Why do I say it's a perfect voltage division problem? We'll look at it, right? We have two resistors and we have a voltage source. So what does voltage division allows us to do? If we have two resistors in a loop and we know the voltage in that loop, all we have to do to find the voltage across one of those resistors is use a formula, and that formula is going to be known as voltage division. So let me write down that formula quickly. That formula is going to be, we can say V1, because we're going to have a voltage here and a voltage here. Now the current is going to be the same, but the voltages are going to be different. So we know we're going to have V1 equals Vs multiplied by the resistor we're trying to find the voltage in. So because we used V1, I'm going to label it R1 over R1 plus R2. So essentially, this is the voltage division formula, right? Now when we look at our circuit, this circuit, we don't have any voltages labeled. So let's do that, right? Because the current is entering the resistor from this side, I'm just going to assume that we're going to have a voltage drop plus the minus, and I'm going to label this voltage as V1. And then as the current comes around, and because the current is going to enter the resistor from this side, I'm going to treat it as a voltage drop from plus to minus, and I'm going to label this voltage V2, because we know these two voltages are going to be different because the resistors have a different value. Okay, so let's find the voltage in V1, which is the voltage across this 2K resistor. Of course, you can use Ohm's law, but the purpose of this is to get us very comfortable with using voltage division. So we're going to say V1, which is the voltage in this 2K resistor, equals Vs. We know Vs is the voltage source. That's going to be 12 volts. Now R1 in this particular circuit is going to be 2K because that is the voltage we're trying to find. So we're going to write 2000. And now we have R1 plus R2, which is going to be 2K plus 4K. 2000 plus 4000. Okay, when we start to simplify this, V1 is going to equal 12 multiplied by 1 over 3. When you simplify that, V1 is going to equal 4 volts. Okay, now that we know the voltage across this resistor, let's find the voltage across this resistor here. Now, of course, I can just subtract, but I'm going to use voltage division for the sake of practice. So to find the voltage across a resistor in a single loop, all you're going to do is you're going to say V2 equals the voltage source we know is 12 over, we're now going to do R2. So this is going to be R2. We know R2 is going to be 4,000 over R1 plus R2, which is 2,000 plus 4,000. When you simplify this, V2 equals 12 multiplied by 2 over 3. Now when you start to simplify this, V2 is going to give you 8 volts. Now, is this our answer? No. They want us to find the voltage VO, not the voltage across this resistor here. So what we did was we just used voltage division to find the voltage across this resistor and this resistor, right? It was good practice. Now let's see what this gave us. So we know the value V2, which is the voltage across this 4K resistor. And we know this 4K resistor came about because we had two resistors in parallel. We had a 6K resistor and a 12K resistor in parallel, which means the voltage V2 is also going to be the same voltage across this 6K and this 6K. I'm just going to write it in, right? So we have V2 here and V2 here. Okay, now that we know the value of V2, we can use Ohm's Law to find the value of I1 in this circuit, and that's what they want us to find, because the question wants us to find the value of I1. Now we know the voltage is going to be 8 volts, so let's use that. Let me just circle these. So we know V1, we know V2. So this voltage was actually helpful to us. So to find I1, we're just going to use Ohm's Law. I1 equals V over R. We know the voltage is going to be 8 volts over the resistor, which is a 6K resistor. So we're going to write it over 6,000. When we solve for this, I1 equals 1.333 milliamp. So that's going to be the value of I1. Okay, now let's solve for the voltage VO, which is the voltage across this 4K resistor. Now there are multiple ways we can find the voltage VO, right? So many different ways. Now because we're trying to learn current division, I'm just going to do the current division route. When I look at this now, I want to find the current I2, because if I find the current I2, I can use that to calculate the voltage across this 4K resistor. Now there are multiple ways we can find the current I2. We can do a KVL loop. We can perform KCL at this node because we know I sub 0 and we know I sub 1. We can just subtract these two, or we can do current division. Now because I want us to get very efficient and be able to see the techniques we can use right away, I'm just going to use current division, right? So I know I2 is going to be this current right here in this branch. Now what does current division say? Current division says you can find the current in any two resistors that are in parallel by using the formula. And that formula for current division is going to be, I'll write it right next to this, and then I'll paste it down. It's going to be I1 equals IS over R2 over R1 plus R2. As you can see, the formula for current division and voltage division is very similar. The only difference is, in voltage division, if you're trying to find the voltage across, let's say across resistor 1, then resistor 1 is going to be on top. But in current division, if you're trying to find the current across the first resistor, which is resistor 1, then resistor 2 is going to be on top. So I'm just going to paste this down. Now we want to find the current I2, right? we can just use this circuit here. We know we're going to have a current source of I sub 0, right? And we know this is the source current because this current is going to enter this node and split both ways. So this has to be the source current. Okay, now we know we want to find the current I2, not I1, because we already found the current I1. So let's find the current I2. We can say, by the way, you can use this to find the current I1 again if you want to compare your answers. I'm just showing you there are so many different ways we can solve these problems, right? But I want to find the current I2. So I'm going to have the current I2 equals IS. Now we know IS is just going to be the source current, and that's going to be this I sub 0 we labeled here. Why? Because we know this current right here is going to enter this node and it's going to split, which means when we add these two currents, this is going to be our source current. So I'm just going to write I sub 0. And we know because we want to find the current in the second resistor, we're now going to write the equation as R1 over R1 plus R2. Right? So if we want to find the current in the second resistor using current division, we must use the first resistor as our numerator, R1. Okay, now let's plug in values. I2 equals I sub 0. We know I sub 0 is 2 milliamp, right? Which we found right here. So we have 2 times 10 to the minus 3 multiplied by R1, which is going to be this resistor here, which is 6K. So we have 6,000 over 6,000 plus the second resistor, which is 12,000. So we have 12,000. Now, before I move on, I want us to see something, right? So some of us might just use this 8K resistor. Now, the thing is, that wouldn't be correct. The reason is because this current does not only flow through this 8K resistor, but the current flows through this 4K resistor. So we had to combine these two. That's how come we was able to get the 12K down here. So now that we have 12,000, let's start to simplify this. We have I2 equals 2 times 10 to the minus 3 multiplied by 1 over 3. Therefore, I2 equals 0.666 milliamp. Okay, so this is the value of the current I2. This might be important to us, so I'm just going to circle it. Now, when we look back up, we know the current I2 in this branch, right? Now, when we look back up at our original circuit diagram, they want us to find the voltage VO. So we know the current I2 that's going to be flowing through this resistor here. So all we're going to do is use Ohm's law to find the voltage VO. So we're going to say VO equals IR. The current flowing through that is going to be I2 times the resistance. VO equals, we know I2 is going to be 0.66 milliamps, or we can just say 2 over 3 times 10 to the minus 3, right? Because we know 0.66 is the same as 2 over 3, that's just the fraction form of it, times the resistance, which is going to be this 4K resistor, so multiplied by 4,000. When you solve for this, VO equals 8 over 3 volts. So this is going to be our answer for the voltage at these two terminals, but also the voltage across this particular resistor, which is a 4K resistor. So this is how we use current and voltage division to find different currents and different voltages in the circuit. Of course, there are many ways we could have solved these problems. I just decided to show you these methods as an introduction to what we're going to be doing in the following videos. So if you have two resistors in series and you know the voltage source, you can use voltage division. Likewise, if you have two resistors in parallel and you know the source current, you can use current division to find the current through each one of those resistors. That's going to be all for now. Stay tuned for the following videos as we work some more examples using current division and voltage division.